Okay, so good morning. I have first to apologize. I'm not an operations manager at our site, so this is not going to be exactly about operations. Hope it may be, and I think there may be some links, but what I'm going to present is a project which has been recently started, which in the overall strategy of the European Commission, you have operators as praise, okay? Then there is development of technologies and systems, and there is centers of excellence. What I'm going to present is a center of excellence, is a project, and this is typically, most of them are about working on applications and improving practices in the use of the parallel machines. Our POP Center of Excellence, this is a project which actually merges or combines partners which happen to be, many of them happen to be at the same time operators of facilities and doing research on some of the topics that we consider are of real relevance for the future use of the machines. So Jülich, as we have seen, Scalaska, HLRS, Aachen, OpenMP, plus service companies in the business of promoting HPC or actually providing service. The idea is partners that with this relationship between infrastructures and research. The idea is to apply the type of research that we do, the type of tools. It's not a project about developing, about further developing, for example, our tools. It's a project about doing service, kind of offering service to external users. And we have structured it about these kind of three types of users. The first type of service, which is about telling somebody, it's like a health check. You go to get a health check and see overall how are you, what are your main issues. And the idea is, can we tell somebody with an application developer or a user about the performance of their application with a small effort? And how far can we go here? There is another type of service which would be kind of second step, which would be try to give actual real detailed suggestions of how to improve, give actual expectations of what they can expect to obtain if they do certain transformations. And then finally, there is a service which is kind of, for those who are not very familiar, for example, with last features of OpenMP or these kind of things, is to help a little bit on that work. It's not to do the parallelization ourselves. So this is the type of studies of services that we are doing. And we are targeting code developers on one side, which might be probably the main customers, let's say, people who write their codes and trying to help identify which are the most productive directions for optimizing a given code. There is another group of users which I think is very important, and we do have that in our facilities. We have people that use third-party codes. The developers of the code claim the code scales very well, and the guys run it and they happen to see it does not scale as well as claimed by the developers. And they're kind of lost because they have not done the code. They know nothing they don't know about it. So the idea is, can you give them indications, arguments they can use in front of the developer to say, okay, this is the fundamental issue, this is the fundamental problem. And can you do that without them being actual knowledge, detailed knowledge of the codes, and ourselves as performance analysts being on the same situation, not knowing about the internals of the code? Can we help them provide this evidence for them to interact with the provider? For part of us as infrastructure operators, also very typical. You have the set of benchmarks that are used to demonstrate that a code scales well, and then the code is run in production with probably different data, which probably exercises different parts of the program and has actually different behavior. So the idea is, can we offer the service to the infrastructure operators to really identify for a real production run what is the situation in performance? And finally, we think that we can provide this service to vendors. They do benchmarking, they do support for the customers, and they actually, for procurements, they have to do dimensionation of the system. So this is the type of customers where we think we can give support. But the whole project is a little bit, as I said, it's not about development. It's more about methodologies. We have Scalaska, we have our tools, or different tools, and actually in reality, if you look at it, we have different methodologies, different ways of doing the analysis. And what we like to do is to really try to work in the integration of those methodologies, keeping the different tools, but still trying to apply those to real production scopes on the real production sides of the customers and get engaged with the customers on this analysis and evaluation iterative structure. And doing that, a little bit, can we do that in 1 month? How far can we go in 1 month with a study? This is the type of things that we want to do. We have just started, so we are in the process of doing our first analysis and the process of individually the different groups that we are involved, trying of comparing really our methodologies. So really I cannot present much results on the project itself. I can explain a little bit on one side, on our side, the type of tools that we have and the type of methodologies that we try to use. So this is what I'll be doing rapidly during the rest of the talk. I will present a little bit about our infrastructures and what we believe should be proper ways of addressing this type of very fast analysis for customers. And what I will be doing is I've been doing the exercise by running one of the Fever mini apps and doing presenting some analysis of that mini app that we have done in the last week. It's a little bit, all of that is a little bit like this. Is this speculative? We are performance analysts. We don't know anything about the application. We just look at the traces and the plots and speculate what can be. And this should be something that should be an iterative loop, which has not happened in this case for this NTChem application. But I'll be making comments on this. So about the infrastructure, the tools that we have a broad infrastructure of instrumentation packages which can generate large traces, but we have mechanisms for filtering and subsetting and reducing the size of those traces. And our main visualizer tool is Paraver, which lets you browse that trace, that performance data. Paraver, you can think of it, is not really a performance analysis tool. It's a DSL for time series data. Okay? And the DSL is programmed, in this case, with what we call the configuration files. It happens to display the metrics, performance metrics on the timelines and tables and profiles, but we have Parameter, which is a non-graphical version of it. That's the same analysis, the only thing is writes plain ASCII text, which can then be scripted and can be put into scripts doing analysis. DMEMAS is the other traditional tool that we have. Essentially, they interoperate. You can compare Paraver traces to DMEMAS simulations of what would happen with different latencies of bandwidths or processor performances. Feedback, generate again Paraver traces, and kind of iterate through this loop of Paraver at DMEMAS. Other thing not so much targeted to application analysis, but more for architects, is the possibility of linking with DMEMAS very fine-grained instruction level simulators, okay, for doing extrapolations for what happens if you have one ISA and you go to a different ISA, or one catch size and you go to different catch sizes. These type of things have a kind of multi-scale simulation methodology, the same that you have in other areas like neurons, for example. So we have this multi-scale simulation methodology at the level of simulating the behavior of the architecture of the system. And finally, we have performance analytics modules, which kind of try to apply analytics techniques to the raw performance data. I'll be explaining a little bit some of these things just very briefly. In terms of tracing, we are trace-based, but we have been working a lot in things like reducing trace sizes. You can have this is an example of visualizing a trace with 1600 cores, 2.5 seconds of a hybrid coupled code, atmosphere and ocean, and still the trace is 27 megabytes. And you can still see a lot of the detail. We typically represent timelines, one row per thread, and the gradient and coloring for metrics like efficiency. In this case, the coloring is light green for low values, dark blue for high values. So this is a region with poor efficiency, this is a region with good efficiency. And here you see the atmosphere and an ocean type of simulation. So this is, you can get a whole bunch, what I said, this is a DSL, this is not really a performance tool, this is a DSL for time series analysis, and by the way, traces are nothing more than time series of events. So you have it's programmable in a sense that it's not hardwired in the tool itself how you build those functions. So if you want to do your own analysis, you do your own kind of derivation of metrics. But well, this is let's say the visualization part of it, of the timelines. The analytics part that I mentioned, we have done a lot of clustering, applying clustering to detect the structure of the computations. And I really did, we typically do this thing. So for every computation between two MPI calls, which is characterized by a given value of instructions and by a given value of IPC, we displayed that those individual computational regions in this performance computational complexity axis. And these points happen to be kind of grouped. You apply a clustering algorithm, you identify a structure in this performance computational complexity space, you project that back to the time and space dimensions of course and time, and you can see structure of behavior along time. This is a basic mechanism to identify a structure, but it's a basic mechanism that can be used, for example, to do something like getting out of a single run of a program all of the hardware counters for every individual region of code with very, very, very precise determination. So you can get instruction mixes, all cache miss ratios, you can get stall causes, all of that out of a single execution of the program. And you can get those metrics for an individual computation burst between exit of an MPI till the entry of the next MPI, which is what we plot here. Or there are other techniques that we do by combining instrumentation and sampling. We end up reporting those same metrics, but at very, 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 very fine granularity. So we have here instruction mixes in red, loads in blue, stores. This is the percentage of loads, percentage of stores, percentage of conditional branches. In black, this line is the instantaneous MIPS rate. Okay? So you can compute instantaneous metrics while only instrumenting at very coarse grain on one side, instrumentation plus sampling also with very coarse frequency of sampling. So minimizing overheads, getting ultra-fine precision. And finally, we have some other tracking techniques. So we have clustering. This is kind of folding analysis, we call it, and this is tracking techniques from image tracking applied to data in this computational complexity and performance space. So these are some of the things that we're using for analysis. The next thing that I would like to explain is about for modeling and for extrapolation. The typical thing, as I said, from a trace, we can apply the non-graphical version of Paraver. We can script it, and we can directly report plots which actually report for every run only 3 numbers. If you see all the previous things, I mean, you will see, oh, there's a lot of colors, very nice, but a lot of complexity, a lot of things to look at. So if you think of performance analysis as a big data problem, and you have huge amount of data you want to squeeze into something, into very few things, which are those very few things? And our proposal is those very few things are only 3 numbers for one run. There is a number between 0 and 1 that is your load balance efficiency. 1 is perfect, 0 would be extremely bad. 1 is your serialization efficiency, and 1 is your transfer efficiency. The product of these 3 things tells you the efficiency of your parallel behavior. So this is kind of the squeezing the whole detail in the trace to 3 single numbers that have semantically meaningful. It tells you, if you, for one application, the tool tells you your load balance is very good, you will probably not spend much time in grouping communications, or you should not. Okay? So this is semantically giving you a little bit indication on which directions to go. The next thing is, you can do that for different core counts, and you can extrapolate, and you can estimate how these behavioral factors will evolve with increased core counts. Okay, and this is a way of kind of identifying which of those factors may not be the bottleneck at the current core counts, but maybe can the bottlenecks at larger core counts. So this is the extrapolation. This is predicting how good the program will scale if you run on the same existing machine that you already have. But this methodology can be applied combined with DMMAS, the simulator of the machine, to estimate what would happen if you were to run this on a machine with faster network or with a faster core, and essentially the idea is from the original traces we can do DMMAS simulations, you can do the same methodology then applied to that, and you can do extrapolations, which, by the way, this provides mechanism to estimate what would be the scalability if you have different latencies and bandwidths, but it's also a way of doing estimations of what will be your performance, for example, if there was no MPI noise or no operating system noise. There are mechanisms in this translation process that let you eliminate that from your traces and do estimates that do not include those things. And the final thing is a continuation of the folding. One of the things that we're doing now is a continuation of the folding mechanism that I described before to get the instantaneous metrics of megaflops or cache miss rates or all of that instantaneous values. We are doing the same thing. We have done the same thing for addresses. So you get the sample version of the instantaneous memory access pattern of your application, right? So this is kind of the tools. What I have now is an example of how we applied some of these tools on some of these things on one of the Fiber mini apps. We applied to a small example. I understand this is a small example. And, well, I'm going to follow a little bit the type of considerations that we think are the type of methodological process that we should follow. In our case, actually, one can look at, the first thing is finding out about the structure. We know nothing about the application. I've not seen the source code. I don't know what it is about. But we need some sort of way of describing in order to have a common communication with the developer. And typically, syntactical structure is the most frequently used presentations. We are personally more in favor on a spatio-temporal structure, so on timelines. Okay, it's telling us the type of activity. You can merge them. You can leave. This is actually a timeline. The color here represents, there's one row per process. The color represents light green means small computations. So there's a small computation intermixed with communications. Dark blue means longer computations, long computations mixed with communications, and orange is very long. Okay. You can link that also to this. You can display the syntactic structure. The line. This view is the source line number from where the MPI calls are made. What I'm trying to say is this is for us the starting point of view. Is the structural time spatial temporal structure. The idea is to identify a region of interest in here, and for us the region of interest typically, I mean, looks like very repetitive. The region of interest will be like that, and typically you would do runs with a few core counts. This happens to be, by the way, a run with 8 MPI processes, but each of them 8-way OpenMP. We are only tracing in this case, and this is one thing that this is on the P machine. We don't have. In our case, we do not instrument the Fujitsu OpenMP, so we can only instrument the MPI. The MPI behaviors only instrument the main thread of the MPI. Still, the application is MPI plus OpenMP. Well, anyway, you can plot the scalability. You can plot and you can say, okay, I'm happy with this scaling. Anyhow, whether you may be happy or not so happy, our methodology or philosophy would be. The important thing would be to go to these 3 numbers that we mentioned. What is the load balance, the serialization, and transfer? And what we have is these numbers here correspond to the measured values for 3 core counts. Okay, so there are numbers between relatively close to 1. At that small core count, the behavior is good. It's fine. It's what we saw in the previous slide. But if you extrapolate those things, then the behavior is going to be a little bit worse. The idea is, what this says, red is load balance. So red is the worst of the three. So when you have a load balance problem, the methodology is first go to these three numbers. Then from these three numbers, try to find out a little bit. If one of them is the important one, try to find out a little bit. So why can we have load imbalance in a computation? The typical way of finding whether we have load imbalance or not, how it's distributed, is by looking at histograms of duration of computations. So this is a histogram of the duration of computations. So we have one row per process. So you have the histogram. So this is very small duration. Somewhere in the trace there are very small in duration. Somewhere in the trace there are these long durations. The more to the right is the longer the duration of those computations. So what you see is that in the long computations, everybody has the same duration except for the first processor. It came out, and it happens at all core counts. It came out that the distribution of load balance is imbalanced, but this imbalance is the first processor that takes more time. Why can a processor take more time in the individual computation bursts than the others? One reason is because it executes more instructions. Is that what happens in this case? Can we see a histogram of the distribution of instructions? This is the histogram of distribution of instructions. Everybody executes the same amount of instructions. Okay, so it's not an imbalance caused by instructions. Other reason, IPC. So can we see an histogram of IPC? Yes. This guy has a little bit worse IPC than the others. Same number, essentially same number of instructions, a little bit worse IPC. Is there any other reason for getting worse, longer duration than other guys? Is there another reason? Well, if you had cache. Well, but cache would reflect in IPC. Okay, so there's another one which is independent would be just core frequency. If you have different core frequencies or effective core frequencies, which means real frequency changes in the processor, or means preemptions, which effectively take out the cycles from you, or means I/O, that you really release the CPU voluntarily. So this is the other potential reason. So can we make a histogram of that metric? And we also see that the effective core frequency seen by the first processor is slightly less, less than the others. Given that the thing is very repetitive, very structured, there's not much variability. The major reason should be, in this case, would be probably voluntarily releases, so it's probably I/O. And actually, with that in mind, we easily found out, yes, that we had compiled the event binary with the debug option, which periodically, the first process periodically prints data, outputs some data. Okay, so we compiled it. The thing is, this is what we had got with that. We compile it without the debug option, and then you repeat the whole process, and you repeat the whole process, and you get some fair improvement in load balance, but still, there was still load imbalance. Transfer still stays important, and serialization efforts appear. Just one very fast going through the type of transfer was important. Okay, the type of simulations that we can do with IMEMAS. This is the nominal bandwidth of the system. This is the time of the nominal bandwidth. How will it behave if you reduce the bandwidth? Well, it starts suffering. How will it behave if you improve the bandwidth? You won't gain that much, a little bit, but really not that much. This is the type of studies that give you hints of how the application behaves in general. Okay. For example, what if you increase not reduce bandwidth, but increase the overhead, the latencies of the messages? This is your nominal case. Will you get better if you get half the latency, or will you get worse if you get 10 times the latency? And the reality is, doesn't matter. If you use a latency for this application which is 40 times bigger, you don't see the effect. Okay. So with this type of overall knowledge, you can look a little bit at the detail, and in the detail it came out. There are some things which are curious, are interesting. It happens to be that the communications are blocked in phases. Well, actually there are a lot of all reduces in here, but there are all reduces that happen to be within the same process. So in this case, I don't know if this is because it's prepared for larger scaling or is used for synchronizing threads inside the process, but the MPI, every process does MPI or reduces on a different communicator. So this is essentially the sequential computation part, and then you have the communications. In the communication pattern is like this, so it's just shifting, rotating a given a given amount of data. And well, from looking at these things, you see that the main reason for why this is timing in waiting for messages. Why is this time here? Is not because of MPI being bad, it's because of load imbalance. This guy taking more time is what delays everybody else. So you identify these additional causes of load imbalance, which were not those caused by the original additional I/O time, but are caused by, well, in reality, if you can count the number, it looks like one thing that was strange is that the granularity was the same when you scale and strong scaling. This is not typically the case. Typically, you get finer granularities when you strong scale. So if it's not the case, what does it mean? It means that it has a given number of bars or blocks or computations to be done, which in this case we counted to 500,000, and they are split to processors. And the way they are split to processors, if the division is even, you will have better load balance than it is not. And then you can, the thing is, by using the non-graphical version, you can generate ASCII tests that you then read with Excel or whatever it is, and you can really see that there is a little bit of load imbalance of that kind. Okay, so there are potentials there. So let me just look at very, very fast at two other things. We have not traced OpenMP, but can we say something about OpenMP without having seen it? And one of the things is we did this tracking technique. So we did the runs with 4, 8, 12, and 16 threads for a given number of MPI processes. And this is, again, putting the data in this computational complexity IPC space. And it comes out that the computational regions for 4 threads have this number of instructions, but have this IPC, which gets worse when you increase the OpenMP activity. Okay, so this is one issue that probably should be looked at with the analysis of the OpenMP detail behavior. So is that IPC gets worse. This movement here, this movement here, if it's a stronger scaling, you would expect certainly to reduce from this number of instructions to half of it. And this happens more or less between 4 and 8, but does not happen between 8 and 16. So there are other things to look at between 8 and 16 that reduce the scalability of the OpenMP, pure OpenMP part. So the point is that you can even say something about things that you have not seen at all of an application that you don't know at all. So I may be missing something, so if some of the developers is interested in discussing, would be probably an interesting topic. And the final thing is this folding technique of getting fine-grained metrics with coarse-grained sampling. This is the result inside one of these small computational regions, which is 7 milliseconds. This is the result of the instantaneous giga instructions per second, or gigaflops, or instantaneous L2 cache misses, instantaneous L1 cache misses. Comes out, the application seems to have 10 iterations inside each of these things. So I'm still again speculating, but seems to have 10 iterations. Seems to have 10 iterations that happen to have concentrated all the cache misses at the beginning of the iterations, or the transitions between iterations. So this kind of generates discussions of would techniques like block prefetchings of the data be applicable? Would techniques like applying, are these 10 iterations independent or parallel, and can nested parallelism be applied? So this is the type of things that we think can be generated in terms of speculating with some sustainable evidence that there might be things to be looked at. So this is essentially the example I had to look at. I wanted to present. What I'm trying to say is that within this project, the POP project, we should try to develop best practices that should be integrated between. So this is too much of our thing. We have then Scalaska, we have another thing. So can we try and, because I understand there should be some kind of underlying fundamental mechanisms and principles that, irrespective of with which tool you look at them, would be the nice ways of presenting applications to performance of applications. So the opportunities, if we have, we're trying to apply this onto applications from the Fiber mini apps running here on Pi. there's the course on Friday that will be presenting some more details on the tools. But applying the tools and mechanisms and discussing and trying to integrating with other tools is something that I think would be interesting. The POP project is kind of the starting point within some of the European partners, but extending that to other sites would probably be very interesting. So, thank you very much.
Thank you very much.